Now on the test, you'll see some questions like this, but they probably won't be this complicated. Let me show you the first one so you'll get a feel for how this works. In these three configurations, we have 4 wires each, and I want to know what is the direction of the magnetic field at the center. And so we do this with our right-hand rule. Remember we had that third application of the right-hand rule? So this wire is out of the page, and so the magnetic field goes in this direction. And so at point P, the magnetic field is tangent to the circle like that. Finger in the direction of the current, and it goes around like that with your right hand. And so these others are very similar. This one, the magnetic field goes in this direction like this, and so at point P, it's like that. And then you can imagine what the others are. For this wire, the magnetic field is going to be like that. And then for this wire, it's going to be like that. So for this one, the net magnetic field, B, at point P, is equal to 0, because those vectors are all equal and opposite. And so I want you to do that. So the answer is not A, obviously, unless they're all the same. But the magnetic field for that one is going to be 0. So what is the magnetic field for configurations B and C? Oh, I'm sorry. Let me start the clicker base. So if you have the answer, go ahead and put it in. Sorry about that. All right. Just do a few more seconds, though. Maybe 10 more seconds. Stop at 20. 20. All right, good. Okay, let's see. I think B is right. So you go through these others. The magnetic field due to this one is into the page, and so it's going to be in this direction. The magnetic field due to this one is into the page. So remember, the current is into the page, so the magnetic field is clockwise, like this. So there, it's in that direction. And then due to these other two, say to this one, is going to look like that, and then due to this wire is going to be in that direction. So you just need to figure out, is the magnetic field clockwise or counterclockwise, and then draw the direction of the magnetic field vector at a point that is tangent to that circle. And I think in option C it was 0, is that right? Yeah, so the vectors look like this, just like they did in option A. So B is the right answer. We'll see that again in the concept test, and you'll probably see a multiple choice question like this, but I'll make it so that it's a little easier, where you just don't have as many wires. It's sort of tedious to go through all these. Morning, Sadie. All right. Let's do a few more clicker questions in the back of your book. I don't remember where we left off. I'm not sure that we've done any since we've gone to this new material. Have we done this one? No, I don't think we have. All right, let's try this. So here we have two particles of the same mass. They enter a magnetic field. It's a mass spectrometer, right? They have the same speed and they follow these paths. So they have the same mass, but which one has the bigger charge? Remember our cyclotron equation, that was that R equals mv over qb. Both particles are entering in down here, and they follow these different paths, and then these are where our detectors are for A and B. All right, let's stop at 105. 105. You'll certainly have a mass spectrometer question on the test coming up. B is right, I think. Let's see, our mass spectrometer our cyclotron equation is R is mv over qb. And so if we solve this for Q, which is really what we want, it's going to be mv over rb. And so the one with the bigger charge is the one with the smaller radius. A smaller radius means that it has a bigger charge. You know, you have a bigger force acting on that one with a bigger charge. It forces it into that tighter circle. You have a bigger centripetal force. And remember also that this comes about from our QVB, that's our force acting as a centripetal force. That's where that comes from. I do want you to know sort of the basics of how a mass spectrometer works. I might ask you just a free response question on the test. How does a mass spectrometer work? What are the signs of these charges? Well, look, my force is to the left. It's going into this magnetic field that's into the page. And so they would be what? Positive or negative particles? They'll be positive particles, that's right. So again, my velocity is initially up, my force is to the left, my magnetic field is into the page, so it's all as it should be in these vectors. That means it's a positive charge. If they were going the other direction, it would be a negative charge. All right, proton enters a uniform magnetic field like this. How does it affect the kinetic energy of the proton? What happens to the kinetic energy of the proton as it enters this mass spectrometer? Remember what centripetal forces do. Kinetic energy is related to the velocity. What do centripetal forces do to the velocity? And then that'll tell you what they do to the kinetic energy. Or more particularly, what do they do to the speed, the magnitude of the velocity? All right, let's stop at 105. 105. Feel free to ask your neighbor, although about half of you have it incorrect. So be careful which neighbor you ask. What?
Did you put in incorrect?
Well, 11 of you have it correct, and 10 of you have it incorrect. Wrong. I just didn't want to say wrong, because that sounds mean. Okay. Let's see. C is right. A centripetal force does what to the velocity? It changes the magnitude or the direction of the velocity, or both. Only the direction. That's what centripetal forces do. So they don't change the kinetic energy. Now listen to that one. She's sharp. All right. It stays the same. Let's do this one. This sort of goes back to what we'd done in the previous chapter, but it's important because, as we said, with the mass spectrometer, you have, and other devices, you have electric fields and magnetic fields that are interacting with one another to cause charges to go in different directions. And you can modulate those electric and magnetic fields. So here we have a beam of electrons that you're sending through an electric field that's already present. It points upwards. And I want to know what is the direction of the magnetic field so that these things go through undeflected. So first of all, remember back to our electric fields. Negative particles feel a force, an electric force, that's the same direction or the opposite direction of the electric field. Negative particles going through an electric field feel an electric force, that is the force due to that electric field, in the same direction or the opposite direction of the field lines. Negative particle, same or opposite direction? Opposite, yeah. It is opposite. That's what you meant to say, right? Yeah, opposite. Positive particles feel a force in the same direction as the electric field. So negative particles would feel an electric force that would be in this direction. So FE is in this direction. If I want these things to go through undeflected, then FB needs to be in this direction. And so that's what I'm going for, is what magnetic field causes this magnetic force, FB. All right, let's stop at 2 minutes. 2 minutes. Okay, well, let's see. Our force is up. Our velocity vector is in this direction. So that means our magnetic field is into the page. So is it C? No, it's not C, because they're electrons. Okay, and so we take whatever, if I have negative particle, it's just opposite. So it's not C, it's D. So probably if you put C, you did it correctly, you just didn't account that they're negative particles at the end. All right, what is the direction of the force on this wire? So you can't really see it very well there, but you can see it better, I think, in your workbook. All right, let's stop at 40. 40. All right, good. He is right. My current is in this direction. Or you can think of, V being in that direction if you want to think back to our previous application of the right-hand rule. B is in this direction, and so it has to be out of the page, E. The force is out of the page. I had this is a little crude, but I'm going to tell it to you anyway, if that's okay. I had this guy who taught me algebra, but he never, let me say I can say this, he never farted around another person. Like, that was his thing. And he did say that he was a private tutor. So am I allowed to use that word? That's crude, isn't it? But that's okay, you've heard worse jokes from me. All right, a horizontal wire carries a current. It's in a magnetic field. What's the direction of the force on the wire? All right, let's stop at 23. 23. Okay, good. C is right because the current and the magnetic field are parallel, but in order to feel a force, they have to be perpendicular, or at least, at some angle to one another. But if they're parallel, then you get J cross J, and J cross J is equal to 0. Because I is in the J direction, B is in the J direction. When you take that cross product, there is no cross product. What's the direction of the net force on this loop? And notice that I have current going in this direction, and in this direction, in this direction, and in this direction. Try not to overthink this one too much. All right, think about what is the net force. What is the sum of all the forces acting on this loop of wire? Good. All right, just a few more seconds. I'll stop at 35, 35. All right, excellent. C is right. Because you have this equal but opposite forces, because your currents are opposite one another. What kind of songs do the planets like to sing? Neptunes? Okay, let's try this one. I'm going to show you this little motor. We've had a similar one to this. This is an electric motor. It's allowed to rotate, by the way. The axis isn't here, but it's allowed to rotate along this axis right here. Current in that direction, current in this direction. And I want to know what is the direction that the loop of wire will turn, at least initially. Remember we taught these electric motors will flip-flop back and forth unless you change the direction of the current. So what direction will this loop of wire turn? All right, let's stop at 55. 55. Okay, I think C is right. You just want to pick one side. We did one of these in class before. Well, let's take the right side. The magnetic field is, or excuse me, the current is into the page. The magnetic field runs from north to south, so my magnetic field is like that. And so current is into the page, magnetic field, and so my force then will be up. So I have an upward force on this side, and then because the current's the opposite direction, I have a downward force on that side. So what's that do to it? Makes it go counterclockwise? Is that what y'all put? Did I do that right? Let me just double check my vectors here. So taking this side, current is into the page. Oh no, I didn't do it right. I'm sorry. Y'all are right, and I was wrong. So my current is into the page, my magnetic field, and so that means that my force is down on this side, and my force is up on the other side. So this force should be down here, and the force is up on this side, making it a clockwise motion. Now look, I brought let me plug this in. You can see it better on the dock cam, I think. I brought a little electric motor a student made a number of years ago. All right, look, so this is a little electric motor. This is the armature. Remember we watched that video about how to make these? This is the armature right here. It's that coil of wire. In fact, it's different from the wire that they use. This is called magnet wire. It has a very thin coating on it. That's just an insulation. And so what they did is you have one that's completely stripped, and then the other is partially stripped on one side, but not stripped on the other. You should use sandpaper to get the coating off. This is called magnet wire. This is what they use for those turns in electric motors. You can get it in different gauges. This is a pretty heavy gauge, just so that it, so it balances better. And then here's the magnets right here. These are just permanent magnets. Notice there's like 8 or 9 of them, just to give you a strong magnetic field. And then down here is the source of power. These are our batteries. They attach to these copper wires, these stiff copper wires, which also act as a cradle for the armature. I'm going to connect the current to it, and then I give it a little jump start just to sort of get over the inertia. I think I'm going the wrong way. It's not perfectly balanced, but it'll go for a while before it stops. So this is an electric motor. You know, we're putting a current through that coil of wire. That actually what's happening is we're generating a magnetic field with that coil of wire, and it's interacting with the magnetic field of the natural magnets, the permanent magnets, and it's causing this motion. But we can think of it also as the current in the loop is experiencing a magnetic force because it's in a magnetic field. And it'll go, until the batteries run out. I said it's not a good science fair project, but there are some cool things if you know a grade school kid that wants to do a science fair project. You can practice around with the number of coils that you use or the amount of current that you use, and then in some way measure the strength of the motor or the torque of the motor. Remember, we can also calculate the torque of this motor in an ideal setting. The torque is given by the number of coils, that's N, times the current that goes through the coils, that's I, times the magnetic field, that's given by these, and then by the area. So if I make my armature bigger, I get a bigger torque. If you want to look at it afterwards, you can. Let's keep going on these. This is probably more akin to what you'll see on your test, not the collection of 4 different wires or 12 different wires. Here we have 2 wires, and I want to know what is the direction of the magnetic field at point P. So I have a wire into the page and a wire out of the page. What is the net magnetic field at point P? So just like what we were doing before, but with only 2 wires and 2 magnetic field vectors. All right, stop at 1 minute. 1 minute. All right, good. C is right. I say you'll probably have one like this on the multiple choice. The one into the page, the magnetic field goes like this. That's this one. And then the one out of the page, right here, is going to go like this. And so my net magnetic field looks like that. Let's take this one over here. Into the page, so my magnetic field goes clockwise. So at this point, it goes in that direction, tangent to that circle. The magnetic field is tangent to that circle. And then similarly for the other one. All right, good. Did y'all do well on that one? Let's see. All right. Oh, shoot. I had a really good boomerang joke. It'll come back to me. We're going to skip this one, okay? This is just like the one we did before. Did y'all get that? Because nobody really laughed. Okay, good. Okay, let's try this. So here I have a wire. Initially there's no current, but then we turn on a current. What happens to the charge on this side? Which direction will a force act? on that charge as it moves through space. So two parts here. Need to determine the direction of the magnetic field created by the wire, and then also what is the direction of the force that's felt by that charge. You could also envision a question on the test where it gives you values for the current and distance and all that, and you can determine the magnitude of the force. But right now, what is the direction of the force? All right, let's stop at 112. 112. All right, let's see. We're sort of all over the board. First of all, the wire, I, creates a magnetic field that's into the page and out of the page. Into the page, out of the page. Let my thumb go in the direction of the current. It goes in, it comes out. So it goes around this wire like this. Now I have this charge traveling in a magnetic field that is out of the page. And then my velocity is up, magnetic field is out of the page, or you can do it like that if you like. So then the force is, what was it, I missed. V is up, magnet is to the, what's that? The right is to the right. Right, so that's the positive x direction. C is right. Alrighty? So you can envision another problem where I ask you, what is that force? And you could calculate the magnetic field. That's that mu naught I over 2 pi r. We saw that. We'll see it again soon because it's going to come back up again. So you can calculate the magnetic field at this point, and then once you know that magnetic field, you could calculate the force given the velocity and the charge just as QVB. So you could actually calculate or determine the actual force that that charge will feel. Say it's an electron or whatever. We'll come back to this. I also do want to tell you about, pull it up. Just a quick little advertisement. Where's our, there it is. We're having this seminar in a week on protein. How do you say this? Kinases? How do you say that word?
Kinase.
Are you guessing?
Yes.
Yes. Okay. All right. Anyway, enzymes, I understand. Protein enzymes and human diseases. This chemist is from Xavier. She's going to be speaking in this room on Tuesday at 4 o'clock. And then just like we had with Dr. Maverick and Dr. Poyman, who also came to speak here this semester, we'll have a reception. There'll be some food, I don't know, cookies or fruit or whatever. It'll be in Beauregard 167. We sort of intended for the chemistry students, but you biology students, you're welcome to come too, especially like you few that are in this class. But I don't expect to be a huge crowd. Okay? I know that last time there was a large crowd, but that's because Dr. Cortez brought her whole class, and I don't think she's going to do that this time. Okay, so y'all come. It's really useful to sit down with these people. Many of you might go to Xavier. We have a lot of alumni that go to Xavier for pharmacy school or even chemistry graduate school. So it's useful to speak with these faculty and see what it's like at these other universities and see what they're doing. And I understand she'll be a good speaker. I'm fairly certain. So come and see what she has to say, okay? Tuesday at 4 o'clock in this room. Reception at 3:15. Understand that Dr. Hollander's class is coming because her cell class, they're studying. Are anybody in her cell class? No, I don't think y'all are quite to that. But anyway, come check it out. All right. So if we have two parallel conductors, this is actually how we define current, uh, based on the force between two parallel conductors. A current carrying wire creates a magnetic field surrounding the wire. So for example, if I consider this wire, as we've seen, it gives a magnetic field that is into the page and out of the page, just like that. And then so this magnetic field extends out into space due to that wire. And we can calculate that magnetic field. That's that B equals mu naught I over 2 pi r. So we can calculate what that magnetic field is based on the distance from the wire and the current that's in the wire. When you put another wire in the field, it experiences a force due to this magnetic field. And we can calculate what that force is. So F12, that is the force, or I'm going to do F21 actually. The force on wire 2 due to particle 1 will be equal to I L cross B. Since these are orthogonal, we'll just do ILB sine theta. So ILB sine of 90, which I'll just leave that off. And since I know that B is equal to this value, I can plug it in there. And so I get, let's keep our I's straight here. This is going to be I2, and this is I1. So I get I2 times L times I1 mu naught I1 over 2 pi r. And so I get this expression for the force on a wire. I'll sort of tidy this up a little bit. We usually write this mu naught L I1 I2 over 2 pi r. And because of Newton's third law, if there is a force, by the way, the direction of the force on this wire is going to be up, right, by a right-hand rule. The force on particle 2, on wire 2, due to wire 1 is up. And in a similar way, the force on wire 1 rather, due to wire 2 is going to be down. That's because of Newton's third law, but you can go through the machinations of our right-hand rule and find that's true, that F21 is equal to the negative of F12. Nice application of Newton's third law. So if they're moving in opposite directions, what is going to be the force that they'll feel? If the currents are in opposite directions, will the wires feel an attractive or repulsive force? Here we've sort of gone through these wires, but what if they're going in opposite directions? The currents, do they feel a force that is attractive, or do they feel a force that's repulsive? A or B? A attractive, B repulsive. All right, let's stop at 35. 35. Okay, A is right. They're going to, wait, no, A is not right. B is right. So if my wires are in opposite directions, then it's going to change the direction of the forces. So up here they were in the same direction, and they were attractive. But if I just switch one of my currents, you can imagine that the forces will be opposite. Like if all I did was just switch the direction of this current, then it's going to change the direction of the force, right? It'll make the direction of the force opposite. And likewise, it's going to change the direction of this force too. So B is right, they're repulsive. Is that clear on what I mean by that? Quite clear? let me step back through this, okay? It's a nice application of what we've been doing. I have two wires. They have currents in the same direction. This wire up here generates a magnetic field. My current I is in that direction, or excuse me, my current I is in that direction, so the magnetic field goes into the page on this side, out of the page on this side. So I get this magnetic field down here that's into the page. Now my current here is in this direction, magnetic field is into the page, so the force is going to be given by this. Now the magnitude of the magnetic field is equal to this mu naught I1 over 2 pi r, where r is the distance of this wire from the first wire. We're not really imagining there being a wire here, we're just trying to calculate what is the magnetic field at this point. So that's my magnetic field, but then when I put this wire into that magnetic field, it actually feels a force. That force, this IL cross B, or I times L times B times sine of 90, gives us this equation where I now plug in this for my magnetic field. And then it simplifies to this expression. We'll further simplify it here in just a second. Actually, no, I don't think so, but in your equation sheet, this is usually how this is expressed. That it's usually expressed as a force per unit length, which is going to be mu naught I1 I2 over 2 pi r. I'm pretty sure that's what it has on your equation sheet. A force per unit length, not just the force, but I could just ask you the force between these wires. Okay? You with me on this? Is it a nod in some way, or a no, or yes? Okay. All right, we define, this is just sort of a bit of trivia, probably not on the exam, but we define the ampere by this. Our ampere, which is 1 coulomb per second. It's hard to measure a coulomb per second, but we define it by the force that particles feel. Right? A galvanometer works by this principle. You have this coil of wire in a magnetic field, and you ask yourself what is the direction, or what is the force that is imparted when you put a certain current through it, and that force is transferred into to measure the actual current. So when you use an ammeter or a galvanometer, you're actually measuring not the actual current, but you're measuring the force that's acting on this coil of wire. So our ampere is defined by this force. If I have two long parallel wires, they're 1 meter apart, and they carry the same current, and if they experience this force per unit length, then we say that current is equal to 1 amp. So sort of a funny way of defining what an ampere is, but it's an easy way to actually have a standard for current, because it's hard to measure the number of coulombs per second. When you think about that, how do we measure the number of coulombs per second that travel through a wire? I mean, you can't really do it. You can't really see the electrons. You can measure the effects of them, and that's what we're doing here. We're measuring the effects of the electrons traveling through wire by measuring the force that is exerted on that wire. All right. Magnetic fields of current loops, just sort of doing a little wrap up here. This is important for solenoid switches. So if you ever see solenoid switches, it's an important application of the magnetic field of a current loop. So first of all, I have a coil of wire. It has a bunch of coils in it. Current goes in a particular direction. Y'all use this in a lab with the what was that, where you measure the magnetic field of the Earth. You use one of these coils like this, where you have multiple turns of wire in a circle. The magnetic field of these is given by this expression, where I is the current, R is the radius, mu naught again is a constant, and N is the number of turns. So if you have multiple turns of wire, then it's given by this. Be careful on this, because this looks a lot like the magnetic field due to a long straight wire. Remember, that one was B equals mu naught I over 2 pi r. Have that pi in there. The way I tell them apart is this doesn't have N. So when we're talking about a single long straight wire, you only have one wire. You're never really going to have more than one wire. But if you're talking about a coil of wire, you're almost always going to have more than one wire. It's possible to have one, but almost always you have multiple turns. It gives you a stronger magnetic field without having to give more current. This is used in a solenoid. Y'all ever heard of a solenoid? On your starter motor of your car, there's a solenoid. And that's what this is. When you turn the ignition on your switch, it engages that solenoid, which has like a little steel piston in it, as I understand. It engages a magnetic field, or a small current to engage a magnetic field, and then that piston is driven into place to set a larger current to your starter motor. That's my understanding of how the solenoid switch. Anybody ever take apart a solenoid on a car? No? I have a video that shows a solenoid switch and sort of describes it in more detail. So let's watch that. Solution. Whenever you have a system where you want to engage a mechanical switch, like in your car on your starter motor, from a distance, like sitting inside your, inside your car. This is a solenoid switch. When you turn on the current, it generates a magnetic field within the solenoid, and then that interacts with a piston or a magnet that's inside of there. That might be it on this chapter, is that right? Yeah, let's do a few more of the clicker questions. We have a couple more minutes, so let's try to wrap these up. And next time we'll start on induction and inductance. If you want to go ahead and start looking at the homework, the solutions are online. Especially if you need a really good grade on this next test, go ahead and start looking at that homework. Oh, did we do that one? I'm sorry. So let's just do this one. I think this is our last one. What is the direction of the magnetic field at the center of point P of this square loop of current? Use your right-hand rule. Just take one side of it. Use your right-hand rule, that third application. You can figure out the direction of the current, the magnetic field at point P. All right, let's stop at 53. Is that out of the page? Yes, E is right. Let our thumb go in the direction of the current, into the page, out of the page, into the page, out of the page. In the center of this solenoid is going to be out of the page. We skipped over that previous one, I'm sorry, but if they're going in the same direction, like we saw before in that example, the two wires will feel an attractive force. Did we miss any others, do you recall? Okay, well, I'll post these online so you can have them, so you can see the explanations for them. So if you're sort of depending on this last exam to bump you up to another letter grade, please go ahead and start at homework for chapter 6 and 7. You might be a little lost right at first, but look at the solutions. It'll help if we move into that chapter on Monday. It's Friday today, okay? Y'all have a great introduction into, what do you call it, gamma phi? Gamma phi beta, that sounds kind of alpha. I'm going to call you gamma phi, okay? Have a great day.